This is Apollo Saturn launch control, T-minus 55 minutes and counting, and the countdown continues to go well.
Cape Kennedy, April 11th, 1970. Launch control. In just a little under an hour, the job of launch control for Apollo 13 will be over.
Now we'll go to the Manned Spacecraft Center in Houston, Texas for a status.
This is Mission Control, Houston. At the present time, the flight controllers here in Mission Control are monitoring the countdown and the status of the crew, the launch vehicle, and the spacecraft.
Half a continent away, the flight controllers prepare for the most critical phase of their job. When Apollo 13 clears the tower, they take over. They are the hub of a worldwide communications and command network, upon which the entire mission revolves. In just a little over 2 days, the men and facilities will be tested as never before.
This is Mission Control, Houston, at T-minus 53 minutes and 20 seconds.
This room, the Mission Operations Control Room, is the most familiar site of the Mission Control Center. But this is just one part of the overall complex. Beyond this are staff support rooms, weather and recovery rooms, voice communications, communications command and telemetry, display control, and the real-time computer complex. The Mission Control Center has two-way information flow around the world to tracking stations, recovery forces, contractor facilities, other NASA and government installations, or wherever else is needed. And of course, to the spacecraft. The link between Mission Control and the spacecraft operates like this. The spacecraft is in Earth orbit, or in lunar orbit, or in space between the Earth and the Moon. It communicates with Earth through one of the tracking stations of the Manned Spaceflight Network. These tracking stations are located at strategic spots around the world to keep in constant contact with the spacecraft. Permanent locations may be supplemented with special tracking aircraft and a tracking ship. The stations are tied in with the Goddard Space Flight Center in Greenbelt, Maryland. From Goddard, the data travel to the Mission Control Center in Houston through two separate routes, one backing up the other in case of a breakdown. There are four basic signals handled by this network. First, tracking data provided by radar. Second, telemetry from the spacecraft, giving the status of the crew and spacecraft systems. Third, voice communications in a two-way flow between the spacecraft and Mission Control. The signals from the spacecraft flow from the tracking station through Goddard to Houston. From Houston, voice communications are maintained, not only with the spacecraft, but with remote stations, aircraft, communication ship, recovery forces, and contractor facilities. The fourth type of signals are command data, going from Mission Control to the spacecraft. These data update the onboard computer with such information as spacecraft attitude, burn duration, and mission sequences. Telemetry and tracking data enter Mission Control through the Communications Command and Telemetry System. These data are then sent to the real-time computer complex. From there, it goes to the Display Control System, and then to man in the staff support rooms, weather, recovery, and the Mission Operations Control Room. Commands are sent from the Mission Operations Control Room through the Communications Command and Telemetry System, through Goddard and the tracking network to the spacecraft. Voice communications are routed through the Voice Communications System for distribution and mission control around the world, in space, or on the Moon. Consoles in the Mission Operations Control Room, staff support rooms, real-time computer complex, and other key locations have panels enabling the operator to select from the many communication loops available. Storage batteries can provide emergency power should an outside power failure occur. All voice communications are recorded for later analysis.
Read out the temperature.
Telemetry signals monitoring the spacecraft systems and experiments are received through the Communications Command and Telemetry System, referred to in NASA shorthand as CCATS. The heart of CCATS consists of 3 UNIVAC 494 computers, 2 of which are active during missions. Telemetry data is received, processed, and distributed on a real-time basis. Digital commands being sent to the spacecraft or experiments go through CCATS, where they are formatted and validated. These commands are then sent to Goddard, where they are again validated and routed to a tracking station to be uplinked to the spacecraft's onboard computer. When the command is received, the verification is then telemetered back to Earth, to Goddard, through the dual paths to CCATS. The time lag from command initiation to the time it leaves Earth is about 1/2 second. The command will reach the spacecraft in from 1 to 3 seconds, depending on its distance from Earth. The return telemetry signal follows the same route in reverse. The bulk of the data are routed through CCATS to the real-time computer complex, called the RTCC. They initially go to the Systems Selector Unit, which can be described as a super switchboard, to send the data to the computers selected for mission support. There are 5 IBM 36075 computers in the RTCC. During an Apollo mission, 2 are used to support the flight. The remaining computers are used to support the Apollo Lunar Surface Experiments Package, an automated lunar science laboratory, and for simulations or other future missions-related activities. They can be called into service as replacements should one of the mission support computers fail. The computer complex is supervised by men in the RTCC control room. The 2 mission computers are both fed the same mission data, but only one is connected to the main display system. The other is a dynamic standby, which can take over immediately should the main computer fail. This switchover has been designed so that a man makes the decision to switch. However, the computer monitors itself to detect internal central processing unit failures or peripheral equipment malfunctions and notifies the operator. While the output of the RTCC is used in several areas, it is primarily sent to the display control system. This area of the Mission Control Center consists of a number of facets. First, the television slide display. This consists of 600 35mm slides displaying various backgrounds. These slides are contained in a cabinet and can be shown over any one of 40 television channels. Images generated directly by the RTCC computer can be mixed with the slide background by the television system. Any display can be called up by flight controllers or others using the digital television system. Should a copy of any display at any given time be desired, a hard copy can be made. This is then sent to the proper location through a pneumatic tube system. Displays of general interest to the flight controllers can be projected on large screens in the front of the Mission Operations Control Room. Rear screen projectors are used, including color and black and white television projectors, slide projectors, and scribing projector plotters controlled by the Mission Operations computer. The staff support rooms, abbreviated SSRs, are the next link in mission control. Located next to the Mission Operations Control Room, there are 6 staff support rooms, including flight dynamics, vehicle systems, life systems, flight director SSR, experiments office, project office SSR, and on the first floor, the instrumentation support team. The general function of all staff support rooms is to receive and analyze data, predict trends, and compare them with baseline data. They send the information with recommendations in condensed form to to the flight controllers in the Mission Operations Control Room, called MOCR. The Project Office SSR provides detailed flight subsystems analysis, where actions to correct malfunctions are called for. The Flight Director's SSR keeps detailed track of stowage lists, spacecraft configurations, and provides procedure support to MOCR. In the life support area, records of medication the crew has taken are kept. Trends in the physiological condition of the crew are analyzed, and medical data requirements formulated. In vehicle systems, the booster is monitored during launch, and all spacecraft systems are watched during the mission, including the command and service modules, lunar module, and EMU, the suits and backpacks which keep the crew alive on the moon. The Experiments Office SSR provides scientific data analysis for operational flight experiments. During lunar surface operations, the ALSEP room monitors the deployment and functioning of the Apollo Lunar Surface Experiments package. This room also operates between missions to observe and control the operation of this automated lunar scientific observatory. The Flight Dynamics Staff Support Room monitors all phases of the flight trajectory and powered maneuvers, such as Earth orbit insertion, translunar insertion, mid-course corrections, and lunar orbit landing and ascent trajectories. The Instrumentation Support Team monitors and controls the flow of all mission data through the Mission Control Center and the Manned Spaceflight Network. All information funnels into flight controllers in the Mission Operations Control Room, MOCR. The men at these consoles must be prepared to make mission-critical decisions. The Booster Systems Engineer, call sign Booster, is responsible for analysis and evaluation of the status and performance of the launch vehicle and its systems. He reports any major malfunction that could affect the mission. The Return to Earth Officer, call sign Retro, observes every phase of the mission from launch through the return, watching for contingencies. His job, in addition to the nominal end of mission planning, is to always have available the fastest and best way to get the crew back in case of an abort. The Flight Dynamics Officer, call sign Fido, makes sure the spacecraft is on the right trajectory, and if it is not, determines the propulsive maneuver necessary to get it there. The Guidance Officer, Guidance, keeps track of the computers on the command and lunar modules to make sure they are functioning properly. His job is especially critical for burns controlled primarily by those computers. The Life Systems Officer, or Surgeon, keeps track of the medical and physiological condition of the flight crew. The Spacecraft Communicator, or CAPCOM, is usually an astronaut, a member of the backup or support crew. He is the only man who talks directly with the mission crew. He receives direction from the flight director on information to be sent to the crew. The Command Service Module Electrical and Environmental Engineer, call sign ECOM, monitors the consumables aboard the spacecraft, projects usage rates, and how long the systems will last. The Command Service Module Guidance and Control Engineer, GNC, keeps track of the status of the propulsion systems and guidance systems components other than the onboard computers. The Lunar Module Electrical and Environmental Engineer, call sign Telmute, serves a similar function to ECOM on the Command Service Module, monitoring the consumables of the Lunar Module, including the EMU, the suit and backpack that keep the astronauts alive while exploring the moon. Likewise, the Lunar Module Control Engineer complements the Command Service Module GNC Engineer, monitoring propulsion systems and non-computer sections of the guidance system of the Lunar Module. At a dual console, the Procedures Officer coordinates activities and data requirements for the flight controllers in MOCR, while the Instrumentation and Communications Engineer, INCO, assures correct operation of the Command and Lunar Module's communications systems. The Flight Activities and Experiments Officer, FAO, keeps the flight plan updated and coordinates inputs to the crew during the mission. He also monitors the progress of experiments and crew activities. The network controller manages all systems around the world not on board the spacecraft. The assistant network controller is in charge of all systems in the Mission Control Center. And this all funnels to one position, the flight director, call sign flight. Working in shifts as the head of several teams of flight controllers, each flight director is responsible for key sections of the mission. Of the 3 or 4 flight directors assigned to a mission, one is designated prime, overseer of the entire flight. The assistant flight director is the flight director's leg man, analyzing trends and being a technical assistant. The 4th row of consoles is not involved in active control of the mission, but serves in several ancillary capacities. The public affairs officer observes the mission, keeps the press and news media informed, and selects television and audio lines to feed the media. The director of flight operations has overall responsibility for all mission planning, flight control, and recovery operations conducted by the Manned Spacecraft Center. He provides policy guidance to the flight director during a mission. The mission director has overall mission responsibility and control of flight test operations. The Department of Defense representative controls all Department of Defense forces connected with the mission, including recovery forces, plus certain communications, and is responsible for search, location, and retrieval of crew and spacecraft. But here is the ultimate responsibility for all decisions made during a flight. Next to MOCR is the recovery room. A miniature version of MOCR, its personnel continually check ahead for contingency planning and to determine the status of the recovery forces. It is responsible for deployment of recovery forces and the return of spacecraft and crew. It takes over the mission once the spacecraft is descending on parachutes. The weather room keeps track of weather trends which could affect launch or recovery. During Earth orbital missions, its functions are particularly important to experiments calling for Earth photography or observation. The Mission Control Center, through the Apollo Simulation Checkout and Training System called ASCATS, can be hooked up to mission simulators at Cape Kennedy and at the Manned Spacecraft Center. This is to aid in training flight crews, flight controllers, and personnel of the tracking stations. Should electrical power fail, a generator plant on-site at the Manned Spacecraft Center can be used to keep mission control operating. But it is in support of a manned mission that mission control comes fully to life.
Yes, that's all right now.
Okay.
Day 21, hour 15, minutes 4, 6 seconds, 5,
Go pick up deviation.
Voice communications. Communications Command and Telemetry, CCATS. RTCC, the Real-Time Computer Complex. Display Control System. Staff Support Rooms. Instrumentation Support Team. Recovery. Weather. MOCR, the Mission Operations Control Room.
We've passed T-minus 30, T-minus 25 seconds and counting, and Apollo 13 is go. T-minus 20 seconds, T-minus 20 seconds and counting. 17, guidance release, 15, 14, 13, 12, 11, 10, 9, 8. Ignition sequence has started. 6, 5, 4, 3, 2, 1, 0. We have commit and we have liftoff at 2:13.
The flight of Apollo 13 provided the ultimate test of mission control.
And it has cleared the tower.
Okay, Todd, I'll have your look.
Looks good here, flight. Good agreement.
Okay, Bruce, how do you look?
S1C looks good, flight.
Okay, Capcom, we go you on the ground.
Cavalry leader, flight.
Roger. Guidance, how's it look?
Good, flight.
Okay, Econ, GNC.
Looks good, flight. Looks good, flight.
Okay, Sergeant.
It looks fine. Through max fuel and we go, flight.
Apollo 13 was routine until 55 hours, 55 minutes into the flight.
Okay, Houston, we've had a problem here.
Flight guidance. Go guidance. We've had a hardware restart. I don't know what it was.
Okay. Houston, we've had a problem. We've had a main B bus undervolt.
You see an AC bus undervolt there, guidance? Or ECOM?
The first thing to do was to make sure that the problem was not an instrumentation failure.
We may have had an instrumentation
Next,
problem.
determine the severity of the problem.
Now, looks to me, you're looking out the hatch, so we are venting something. We are venting something out into space.
Okay, let's everybody think of the kind of things we'd be venting. GNC, you get anything that looks abnormal in your system?
Negative flight.
How about you, ECOM?
That's a firm flight. Flight, I've got a feeling we've lost 2 fuel cells. I hate to put it that way, but I don't know why we've lost them. It doesn't all tag up.
Network from Flight. Flight Network. Bring me up another computer in the RTCC, will you? GNC, can you get somebody in the back room to try to figure out what the equivalent delta V is we're getting so that we can see if we can backtrack to see if we can figure out what's venting.
It would later be found that an oxygen bottle in the service module had exploded. The decision, power down the command and service modules and use the lunar module as a lifeboat.
Tell me you from Flight. Go ahead, Flight. I want you to get some guys figuring out minimum power in the LEM to sustain life.
It was now up to mission control to get the astronauts back. Because of their position between the Earth and Moon and the condition of their systems, the crew would have to loop around the Moon, then head home. They were living in the lunar module, dependent on systems not originally designed for long-duration spaceflight. The object, survival. Booster, his job was over now. Retro, get them back to the recovery area in the best way. Fido, figure the best trajectory and the maneuvers necessary to do it. Guidance, keep that lunar module onboard computer honest. Surgeon, make sure the crew stays okay. Capcom, keep the information coming to the crew. Update those checklists. ECOM, monitor the systems and make sure we have enough left in the command module for re-entry. GNC, make sure we have attitude and guidance for the mid-course burns and re-entry. Telmu, watch the lunar module consumables. Keep the crew alive. LEM control, make sure the lunar module has attitude control, guidance, and propulsion to make the burns to get home. Procedures, keep the MOCR functioning smoothly in this crisis. INCO, maintain communications with the spacecraft. FAO, update the flight plan. Make sure the crew has time to get things done. And give them some time to eat and sleep. Network, keep the Earth-based systems functioning. In mission control alone, 10,000 miles of interconnecting wire and 2 million connections. Flight directors, it's on your back now. If you're not on duty, you're sleeping. You're in meetings to make survival decisions, or you're running simulations to develop spacecraft procedures and techniques. Staff support rooms, get cracking on the innumerable details involved. Recovery, weather, make sure they'll land in a safe area where you can get to them. Display, keep the information in front of the men who need it when they need it. RTCC, calculate, recalculate, and calculate again. Where are we? Where should we be? How do we get there? Instrumentation support team, keep the telemetry coming in and the commands going up to the spacecraft. ASCATs, get the simulators cranked up. There's hundreds of new emergency procedures now. They must be tried on Earth before the crew uses them on their crippled spacecraft. Voice communications. Patch in everyone around the world who needs in. Keep them in touch. Then, 4 days after the accident, the crew jettisoned the service module to prepare for re-entry.
And there's one whole side of that spacecraft missing.
Is that right?
The whole panel is blown out, almost from the base to the engine.
Really a mess. Man, that's unbelievable.
Then they jettisoned the lunar module that had been their home since the accident and made their re-entry.
Odyssey Houston, we show you on the mains. It really looks great.
They got back. Mission Control had done its job. Not just a collection of sophisticated electronics. For these devices are there to serve one purpose: to get the information to the man who needs it, when he needs it. For men must make the ultimate decisions. And they are Mission Control.